So hi there, my name is Seri. I'm VP of Research at Armis, and today with me is Greg, a researcher on my team. And today we're going to talk about several methods that we've explored to exploit packet-in-packet attacks in Ethernet. These types of attacks can allow attackers to bypass network perimeter security, such as NATs and firewalls. So we'll get to how this can be done in a minute, but first let me tell you a bit about ourselves. The company we both work at, Armis, is an IoT security company that focuses on providing visibility into the behavior of unmanaged devices in enterprise networks, medical facilities, and manufacturing environments. Researching embedded devices and wireless communications led us to some interesting discoveries in recent years, which we presented in previous Black Hat talks. These included Blueborn, which was a set of Bluetooth vulnerabilities in a wide array of operating systems, Version 11, a set of zero-day vulnerabilities in TCP IP stack used by VxWorks, the most popular real-time operating system, and most recently, CDPON, Layer 2 RCEs in various Cisco devices. Okay, so before we dive into the actual findings of our new research, let's begin with the motivation that led us to it. As many of you probably know, the majority of zero-click remote code execution vulnerabilities require attackers some form of network adjacency to the victim device, either direct IP routing or even layer 2 access. This includes some of the RCs that we've discovered ourselves, such as Urgent 11 and CDPON. But this is also true for other well-known RCs, such as Bluekeep and even Eternal Blue. Moreover, certain vulnerabilities, and again, CDPON and Urgent 11 are examples of this, can even be exploited with a single packet if only the attacker could send a fully controlled packet to the victim device from beyond its network perimeter security. Amusingly, some guy on Twitter that you might have heard of him posted this tweet a while back, and this naturally piqued our interest. So this is kind of the NAT bypass we exactly wanted to investigate. However, it's probably fair to estimate that the solution that we've came across is very different from what Sammy had in mind. Okay, so let's consider the following scenario. An attacker is behind a firewall and a NAT somewhere on the internet, and his objective is to inject layer 2 packets into the internal subnet, this network segment on the left, that lays in the inner side of the firewall. The purpose of the NAT, that is also acting as a firewall on the edge of this network, is to allow outgoing connections to the internet and block anything else from entering the network. The NAT accomplishes this by creating firewall rules on the fly to allow passage of packets returning from target servers of these outgoing connections. This behavior is called allowing related and established packets, that is, packets that are part of or related to existing TCP or UDP sessions. This means that usually an attacker is able to send packets into this target segment only when a TCP or UDP session is established to a server that he controls on the internet. And even when this does occur, he would only be able to control the payload of the application layer in the packets that return to the network, and could not fully control the packet's headers. Obviously, this wouldn't allow him to send arbitrary layer 2 or layer 3 packets, and blocking arbitrary packets is what firewall is there to prevent. If only there were some way to somehow send packets within packets, some way to pass malicious packets within legitimate packets. That would magically, and these some way would magically transform once they pass the firewall. That will be amazing. And yes, you've guessed correctly, this concept is called packet-in-packet. The term was probably first coined by Travis Goodspeed back in 2011 when he discovered a way to inject fully controlled layer 2 packets in Zigbee and in Wi-Fi, given the ability to send packets with partially controlled payloads. This sounds quite surprising, and it relies on the fact that wireless transmissions are inherently unreliable, and this guarantees that bit flips would randomly occur in transmissions, and eventually the headers of the lower layers of the packet may get corrupted. When this occurs, the receiver of such a packet can be fooled to interpret the payload of the packet as an entirely new packet, including the previously uncontrolled low-level headers. An attacker that has the ability to even partially control the payload of such packets may be able to inject fully controlled layer 2 packets. In the example here, A7 is the sync word of the layer 2 protocol used by Zigbee, and when it gets corrupted, the receiver will continue searching for another preamble and sync word inside the packet. A crafted payload that contains these magic numbers will get interpreted from that point on as a completely new packet. A more recent packet-in-packet attack was devised in 2015 for non-encrypted Wi-Fi. This one targeted the MAC frame aggregation feature of Wi-Fi access points using a different technique but with a similar concept. partially controlled packet payloads together with bit flips occurring randomly in the air results in arbitrary packet injection. So the concept of packet-in-packet attack isn't new, but it was mainly explored in wireless protocols. In our case, however, we wanted to bypass firewalls, and these are connected to wired networks. Does it even make sense for this to work on wired protocols? So let's dive deeper to the physical attributes of Ethernet. The most popular Ethernet cables are copper cables that use either fast Ethernet, which is 100 megabits, or gigabit Ethernet. These two PHYs have very different encodings on the physical layer. In fast Ethernet, the encoding uses 5-bit symbols on the wire for every 4 bits of data. This leaves space for additional control symbols such as start and end of frame. The rest of the symbols are invalid. Gigabit encoding is different, but it also uses a similar approach where it has a start and end of frame symbol. The important thing to understand is that there is no error detection at this layer except for detecting invalid signals. An Ethernet cable is never connected directly to a CPU or microcontroller, but rather it's usually connected to an Ethernet PHY chip. That PHY chip is usually connected to the CPU using a hardware interface called GMII or RGMII. The job of the PHY chip is to translate the Ethernet symbols from the wire into a parallel 8-bit bus carrying our familiar layer 2 data bytes, alongside the RX data valid signal used for delimiting the frames. So while on the PHY layer, special start and end of frame symbols are used to delimit Ethernet frames, on the GMII bus, these explicit signals only affect the RX data valid signal, and that signal is only part of what the MAC layer and the CPU uses to delimit a frame. We'll see this in a moment. Here we can see what data actually appears on the wire as part of the Ethernet frame and how it's handled via the different layers. First, a start symbol appears on the wire. This causes the PHY chip to raise the RxDV line, indicating that there is an incoming frame. Then symbols are converted to data bytes. However, the first byte of this data isn't actually the layer 2 bytes that you're used to seeing in Ethernet frames in Wireshark, but rather they begin with the preamble sequence and the start of frame delimiter, an SFD byte. The value of this byte is D5. The CPU, when seeing the RxDV line go high, starts waiting for an SFD byte on the RxD port. All bytes before that are treated as the preamble. After these initial bytes comes a familiar layer 2 payload, which is the Ethernet frame starting from its headers and up to the payload. When the end of frame symbol arrives on the wire, the RxDV line goes low and indicates to the CPU that the last 4 data bytes are again not actually data, but rather a CRC32 of the entire received frame. The most important thing to note is what verifies the CRC32, this FCS, is actually the CPU rather than the PHY chip, meaning potentially corrupted frames may arrive all this way to the CPU without being dropped on the way. So now let's see why this design is susceptible to a packet-in-packet attack. Suppose the SFD of a packet got corrupted on the wire. So in this case, the D5 byte got corrupted and turned, for example, into a D4. The CPU sees the RxDV line go high and starts looking for an SFD byte. It won't find the corrupted byte, so it will keep searching. If the packet was specially crafted, the attacker could place a D5 somewhere inside the packet payload. If this is the first D5 in the frame, it will be picked up as the SFD. All the previous bytes will be considered to be the preamble. In all the implementations that we've tested, we didn't find any that limit the length of this preamble sequence or even check its value. Therefore, if an attacker can place the first D5 byte in the frame, a packet-in-packet condition will occur. The only condition is that the corrupted symbol must become some other valid data symbol. More importantly, the CRC at the end of the frame must now be correct for both the original packet and the new inner packet. So again, this is what the original outer packet looks like. First, there is the corrupted SFD, then there are the headers and the payload, which in this case is attacker controlled. Finally, there is an FCS, which is the CRC32 of the whole packet starting from the Ethernet frame. Here the attacker has placed the D5 in the payload, which now became the new SFD. Therefore, in the following bytes, all the following bytes represent a whole new Ethernet frame. We'll call this the inner packet. Again, the inner packet is a whole layer 2 packet with headers and all. The big limitation of the attacker, however, is the fact that the CRC of the inner packet must be identical to the CRC of the original packet. Therefore, the attacker must know the exact contents of the headers of the original outer packet. This includes source and dest MAC addresses and internal IPs. These are not usually visible from the outside of the victim network, and the attacker will have to find those in advance. Creating the CRC32 collision between the outer and inner packets is trivial as long as the entire contents of the outer packet is known. This can be done by adding a 4-byte complement value that can be calculated in advance before the inner packet. In this way, the CRC of the outer packet can be forced to become anything we want. In this case, we'll make it the same CRC as the inner packet, which allows the inner packet to be fully controlled. The method of how to calculate this complement is well known, and we won't dive into the specifics of it in this talk. So all of this sounds kind of surprising in a how did we never hear of this before kind of way. But actually, it isn't completely new. There was a talk back at 2013 that presented this exact issue. However, the researcher concluded back then that wired Ethernet cables are too reliable for the required corruption to actually occur. However, looking at the standard, for example, of gigabit Ethernet, there is an acceptable bit error rate in the standard specified for Cat5e cables. The value mentioned is 1 corrupted bit for every 10 billion bits on the wire. So if, for example, an attacker can send 10 gigabits of data on a gigabit Ethernet cable, a bit flip would actually occur after 10 seconds. And this is what is considered to be the industry standard. So we set out to find what is actually the bit error rate of cables in actual networks. As you see here, for example, on Cisco switches, you can query the amount of symbol errors and CRC errors on each port of a network switch. You can also query the total amounts of valid packets that pass through the port, and use it to calculate the average bit error rate for each port. In Armis, the company we both work at, we manage very large enterprise networks, and that gives us access to anonymized data coming from switches. And we performed a survey, and for example, here are 2 very large networks. Both of them have tens of thousands of active switch ports. And not surprisingly, 90% of these ports don't experience any errors. However, about 1% of them do experience the standard acceptable bit error rate of 1 in 10 billion bits, and 0.3% of them experience 2 orders of magnitude more errors, and that's a significant amount of bit flips. In the cables that have this error rate of 1 in 100 billion bits, a packet-in-packet collision can occur within minutes. And this is already considering that the attack requires that a bit flip occurs on a certain byte within the frame rather than just any byte on the SFD byte. From this data, it's not possible to know exactly what's the source of the corruption in the ports. Whether it's the cables, the connectors, the sockets, any of them can be physically faulty. However, for the attacker, it's not important which part is faulty. The attack will work regardless. So now Greg is going to describe some of our efforts to better understand the underlying causes of these faults.
So hi, I'm Greg, and now we're going to dive into our theory of what's behind those bit flips and how we can reproduce them. So as Ben mentioned, Cat5e cables have a standard acceptable error rate of 1 in 10 billion bits. But in practice, by actually experimenting, it's easy to see that the error rate varies greatly between cables. Short cables, let's say 10 meters or so, pretty much never experience any errors. Long cables, the longest defined to be 90 meters long, will experience something in the vicinity of the standard acceptable error rate that was mentioned before. In practice, usually less. However, faulty cables of any length can experience orders of magnitude higher error rate. What we refer to as Ethernet cables are actually a multitude of different cables, but we focus on Cat5 and Cat6 cables in this research. And these cables also have a parameter that specifies their shielding. UTP means unshielding, and FTP and STP cables do have shielding. Now, any of these cables can be just as faulty as any other. It's just not as equally likely. From what we've seen, though, the main parameter determining the likelihood of a fault is actually the length of the cable. So what's inside those cables, really? A UTP cable is basically just 4 tightly twisted pairs of wires running the length of the cable. If we oversimplify a bit, each of the 2 wires in each pair will be always set to the opposite voltage of the other wire. And the signal is the difference between the voltages. A positive difference is a 1 bit, and a negative difference is a 0 bit. In this way, any outside interference should affect both wires of the pair in the same way and at the same time. Therefore, whatever in the interference, the difference between the wires should remain the same, and the signal should remain intact. But as is the case with everything in nature, those twisted pairs are not perfect. And therefore, STP and FTP cables have additional shielding to further prevent interference. And any further imperfection beyond that in such cables allows weaker and weaker interference to get through and damage the signal. So we went around our offices and looked for faulty cables. And here's one example. The device is a fluke cable qualification tester. It can be used to detect and classify cabling faults. In this case, it's connected to a fairly long, almost 90-meter cable. And the shield of the cable is not connected, as the test reports, even though it does have a shield internally. Also, it reports that at least one of the pairs has an impedance that's too high, even though the cable is still under the allowed 90 meters. So this cable is faulty and indeed has an elevated bit error rate. Another example is this relatively short cable that has a very high error rate. The fluke reports that there is a bridge tap, which in this case really just means that there is a short between some of the pairs inside the cable. And the cable only works at fast Ethernet speeds because fast Ethernet only uses 2 out of the 4 pairs inside the cable. So in this case, wire number 8 here just acts as an antenna, basically that collects interference into wire number 1, which actually is in use. This one obviously fails to work as a gigabit cable, but since there is an auto-negotiation procedure, the switch port will fall back to fast Ethernet when this cable is attached. So this cable obviously has a very high error rate, and such that the attack actually works in seconds on this cable. So there isn't much point in showing you cables off our office floor, so let's do something more scientific and show a way to reproduce the condition. So our goal here is to create a cable that's faulty enough to have a high error rate, but not faulty enough to just fail to work entirely. And that's pretty difficult to do reproducibly, but we found a few methods. The most reliable do-it-yourself method isn't exactly a cable, but rather 2 cables that interfere with each other. Both cables have a fault where one of the pairs is untwisted quite a bit, and this allows interference to get into the pair, but also to be emanated out of the pair. So 2 adjacent cables with such a fault will interfere with each other. This is obviously a highly, highly exaggerated fault, and this is not how a fault like that would look like in any way. However, this fault does simulate a real condition called alien crosstalk, where 2 cables interfere with each other. This sometimes happens in long runs of parallel cables. Realism aside, what's shown here is very convenient for production purposes, since the error level can be adjusted by the distance between the 2 untwisted pairs. And of course, the resulting errors are no different to other more realistic kinds of faults. This will work for cables carrying gigabit Ethernet. For fast Ethernet, it's a bit different, but requires only 1 cable. In that case, it can interfere with itself between its TX and RX pairs. So this is the output of a device called an electrical network analyzer, which measures the signal loss and reflections inside transmission lines, in our case, Ethernet cables. The signal loss is graphed against a frequency range of 50 to 200 megahertz, which is the ballpark range for Ethernet. This particular graph shows the signal loss between the 2 untwisted pairs from the previous slide. You can see here that there is only about 25 decibels of signal loss from the aggressor to the victim cable. The standard specifies actually that 24 decibels is the expected loss in a 90-meter cable. So this interference is pretty much just as strong as the single in a very long cable. So another do-it-yourself fault, this time a bit more realistic. One of the pairs here is shorted to the aluminum foil shield that surrounds an FTP cable on the inside. Among all possible cabling shorts, this is probably the most likely one. In this case, we just solder one of the pairs to the shield to have a reliable condition. Obviously, in a real cable, this kind of short can disappear or reappear if you bend or flex the cable. So in this case, the shield is electrically connected to 1/2 of a pair, essentially acting like an antenna. This will allow interference from outside and even reflected signals to mess with the original signal in the pair. So here on the top graph, we can see a trace that shows the signal attenuation in a normal 60-meter cable. And on the bottom graph, we connect that 60-meter cable to the 2-meter shield-shorted cable from the previous slide in series. And I'll explain what I mean by that in a bit. Now, as you can see, the result is an additional 10 dBs of attenuation. It's far more than a 2-meter cable should cause. And there are, of course, other kinds of cabling faults, like partially torn wires, that we simply don't have time to cover. So about connecting cables in series. This sounds strange, but actually that's what's usually the case. Let's picture a model scenario for how the device is commonly connected via cables. The device is in fact rarely connected by one cable directly to a switch, but rather it's connected via multiple cable segments, C1 through C3 on this slide, that electrically speaking constitute one cable. Now, with regards to bit flips, they happen due to a combination of factors. First, there needs to be high signal attenuation in the cable, and this is caused by long cables and is not a fault in itself. Then there does need to be a fault somewhere in this chain that allows some interference to get through. And finally, there needs to be a source of electromagnetic interference, or EMI, that affects the faulty region of the cable. These actually occur naturally from nearby equipment or cabling. So for bit flips to occur, you basically need a long faulty cable. However, as you can see in this case, C2 here can be long, and C1, for example, can be faulty. So together, the combined cable C1, C2 is now a long faulty cable. So let's clarify. Our attack consists of sending lots and lots of packets that encapsulate the packet-in-packet payload as fast as possible over the faulty cable. The attacker will then wait for a bit flip to occur in the right place, which is only SFD byte. The odds of this decrease with the length of the attack packet, so the attacker will choose shorter packets in order to have more SFD bytes on the wire. Basically, all of this means that an attacker can only reasonably hope to inject one packet in an attack that could take hours. So what single packet can do the most damage? And there have been certain single packet RCEs, like our Urgent 11 or CD-PON attack that Ben mentioned in the beginning. There are also some rare examples, like a 2018 memory corruption in Apple's XNU kernel that could DOS basically all Apple devices back then. But there are also some packets that are problematic by design. Let's look at an IPv6 router advertisement RA packet. This is kind of like a DHCP offer, but for IPv6. And just like DHCP on IPv4, this packet can tell the receiver how to set up their IPv6 routing table, DNS servers, and also search domain, which on Windows can be interesting. For instance, this will allow the attacker to configure the Windows Automatic Proxy Discovery feature and configure a proxy server for all HTTP traffic. So this is what an injection of such an array packet would look like. On the left, you see a benign UDP packet, of which there are lots. You only see one. On the right, you see an array packet after a bit flip happened on the SFD byte of the original packet. And as you can see, the injected packet is broadcast. And obviously, it can be any packet as we fully control it, including the layer 2 header. This packet will be received by everything that's downstream from the faulty cable. In case you didn't know, IPv6 is almost always enabled on every interface of every modern device. There doesn't need to be a working IPv6 network for this to work. And the array packet is different to the familiar DHCP of IPv4 by not being a request-response protocol. In DHCP, a device usually requests configuration and then waits for a response. With array packets, all devices just constantly listen for unsolicited array packets. And this is kind of like the ancient pre-DHCP reverse ARP protocol. In the array packet, as you can see here, an attacker can add DNS servers to the victim and also set the search domain. Now, you'd think this will only be limited to IPv6 DNS servers. However, there's a feature of IPv6 addresses called IPv6 mapped IPv4 addresses, where actual IPv4 addresses are mapped onto the IPv6 address space. And the intent is to actually use the IPv4 protocol to reach them. So even though it's technically an IPv6 address here, these are actually really IPv4 DNS servers and will be used as such. Also on Windows, the Windows Automatic Proxy Discovery feature will try to download a configuration file from wpad.attacker domain if attacker domain is set to be the search domain. And this feature is still on by default in Windows, even in 2020. So now we're going to do a demo, and Ben will take you through it.
We're going to show a demo of this attack. In this scenario, the attacker has prior knowledge of the network, including MAC addresses and where the faulty cable actually lies. So this has some prerequisites. The attack scenario is a one-click, so the victim is coerced to click on a certain link that will lead their browser to send a UDP packet to the attacker, causing the NAT to allow incoming traffic for the established connection. The attacker will abuse this by sending many UDP packets back to the victim. A bit flip would eventually occur on the faulty cable, leading to the packet-in-packet condition. Lastly, this injected packet will be this IPv6 router advertising packet that we've just discussed. And we'll show this in the terminal, and I'll explain throughout what's actually taking place. Okay, so what we have here is a simulation of the network that we seen in the previous slide. On this edge is the firewall, the NAT. So this is the edge of the network, and here that's the internet. And then after it, we have a core switch, and that connects through this this faulty cable. This is the worst cable that we can find in our office, to an access switch. And this access switch has this internal segment, and to it connects this Windows device, and this device will be our victim. Okay, so on the right, we have the attacker's terminal. On the bottom part of his terminal, we'll have a packet capture of the attack from his point of view. And on the left, we have a VNC to the Windows device, which is the victim device, located inside the internal segment. First, we can see that the faulty cable has an impact on the network performance of this device, but not a very significant effect. So there is some packet loss, but not a lot. And now we can launch the attack. The attacker launches an ambush script with the MAC addresses that he found in advance. And the victim will enter a link that will take him to the attacker's web page. The attacker will then send all these UDP packets back to the target. Some of them would bit flip, and we can see in the Wireshark on the Windows device that they've turned into this wire advertising packet, again, due to the packet-in-packet attack. And this wire advertising packet registered this DNS search domain on the Windows device. And this would be used for the Windows proxy auto-discovery feature. So when Greg there went to Google.com, he actually got this pond page. Okay, cool.
Okay, so the biggest problem with this attack is that the attacker needs to know the internal MAC addresses that appear in the packet headers. Otherwise, they can't calculate the CRC complement. These internal MACs are not visible from outside of the LAN. However, they're not a secret, and they were never designed to be a secret. In some cases, it's easy to guess them. For instance, in a non-internet scenario, let's say for an attacker in a DMZ, one interface of the firewall is directly visible. And as is the case with most network equipment, the MAC addresses of all the interfaces of the same equipment are adjacent. So it's easy to guess the rest of them knowing just one. Better yet, if you look at Wi-Fi, even on encrypted WPA2 network, the MAC addresses appear in plain text over the air. And they can be picked up by sniffing in monitor mode in physical proximity to the network. These MACs are the same exact MACs as on the wired network. It's fairly common for organizations to bridge their access points directly to their wired networks. So for example, the MACs of the default gateway will be visible in the air, even though it's not even a wireless device. What's more is that MAC addresses never change. If an attacker physically arrives on site once to collect MAC addresses, these will remain correct forever. If you sniff Wi-Fi in monitor mode, this is what you'd see. Even though the data is encrypted, here you have 5 MAC addresses per packet in plain text, of which one is always the MAC of the wireless device, and another is always the MAC of another device on the network, be it wired or wireless. In this case, you have a Xiaomi phone talking to a Fortinet firewall, which is its default gateway to the internet. These are the 2 MACs that appear in any Ethernet packet coming from the firewall to the device when traveling on the wired network on the way to the access point. So now it's actually time for the fun part of this talk. And we talked about how faulty cables are cables that are susceptible to reasonable electromagnetic interference. However, what about unreasonable interference? An unshielded cable, even if not faulty in itself, given an already attenuated signal, should become susceptible at higher interference levels. And surely you may know that EMP weapons are a thing. These are designed to kill electronic circuits at a distance. They operate by sending very short but very powerful wideband bursts of radio, commonly in the 100 megahertz to 2 gigahertz range. The wavelengths of this range just about match the lengths of wiring inside various equipment. And at those power levels, any such wire becomes an antenna, and so will apply voltages to random parts of circuits. With high enough power, this is meant to fry all sorts of electronics. Now, we don't need to fry anything. All we need is to disrupt already weak attenuated signals. Therefore, the same thing will work for us at much more reasonable power levels. So finding public research into EMP devices online isn't exactly easy. However, if you refer to this as an EMP simulation, you can get all sorts of results. These separate papers all talk about creating a fairly similar device. Basically, they charge a capacitor to 500,000 volts and then discharge it through a fast spark gap in parallel to an antenna. And this creates a very short, under 1 nanosecond pulse with a power level close to a gigawatt. And this kind of pulse will appear as a powerful wideband radio burst when radiated from a proper antenna. But all we need, for the sake of demonstrating the phenomenon, is simply the oldest kind of radio transmitter that was invented in the late 19th century. And this works the same way. A capacitor is discharged through a spark gap, only far lower voltage is used in the range of 10,000 volts. And a simple open-air spark gap is used. This kind of transmitter is a powerful source of interference in the 50 to 150 megahertz range. This is what the transmission spectrum of our device looks like. A wideband pulse between 50 and 120 megahertz. The actual power level is much higher than shown here, since the pulses are very short, and this is averaged over time. This is the kind of interference an oscilloscope probe loop, which is not connected to anything, will experience at a distance of 2.5 meters from our device. You can see that the main frequency is indeed around 80 megahertz, and about 600 millivolts are induced in the wire. Now, attenuated Ethernet signals have voltage levels in the range of 100 to 200 millivolts. So it's reasonable to expect this interference to affect the signal. And on a 10-meter long unshielded Cat6 cable, 2 meters from the device, we can also see that not only are voltages induced, but they're also different enough between the wires of each pair such that they affect the differential signal, as again, the pairs are imperfect. And this is shown in purple on the graph. Now, this is what guarantees bit flips to actually happen. OK, now we're going to show a demo of the proximity attack, and Ben will take you through this.
OK, so this last demo is a proximity attack. In this scenario, the attacker is physically near a Wi-Fi access point, and his objective is to induce bit errors in the Ethernet cable that is connected to it, which is unshielded but not faulty. As Greg explained before, the attacker is able to collect the MAC addresses of the victim and NAT via Wi-Fi monitor mode. Then, when sending a burst of crafted packets from the internet, the attacker will use the EMP device at the same time. This will cause bit errors on the AP's Ethernet cable, which will lead to a packet-in-packet attack, even though the cable is not faulty. Lastly, the injected packet is the same IPv6 RA packet that set up a search domain on any Windows machine connected to the AP. And we'll show this now in an actual video that we pre-recorded. OK, so this is the setup from the previous slide. This was shot in a bomb shelter. Just so this will be like an ad hoc Faraday cage of this setup. We have an access point here. We have a Windows device, the victim that is connected to it via Wi-Fi. There is this long Ethernet cable, the blue cable, that is connected to the access point. And this cable will be targeted in the EMP attack, causing bit flips on it. It's a non-shielded but not faulty cable. And Greg, the attacker here, will be launching the attack. Here we can see a close-up of the EMP device. And here we can see how it looks when it's turned on. And we can see this attack now. We'll have this Windows device here. Initially, we can see that it doesn't have a search domain configured on it. Once the attack succeeds, it will have it. And Greg will launch the attack, sending the burst of UDP packets, and simultaneously turn on the EMP device. And we can see the router advertising packets have been injected via the packet attack in the Wireshark, and we can also see that the search domain has now been registered for this device. Okay, and we have really a limited time, and so we tried to talk quickly through a lot of material, but I wanted to conclude on a few notes for this talk.
before we get to your questions. First of all, yes, it seems that Ethernet packet attacks are possible. It's not a simple attack, and we saw that it has a couple of prerequisites. But nevertheless, we were surprised to find out that it was more practical and more real than we ever thought about. And then there needs to be some way to eventually handle this issue. There shouldn't be a reason for Ethernet to have this problem, although, as seen in previous research, preventing packet-in-packet attacks is quite a difficult task. We also have a blog about this with more information on our website. It's in the link here, and we'll be happy to answer any questions that you have now. Thank you.
There.
Hi, guys. We hope you enjoyed the talk. If you have any questions, we'll be happy to answer now. And yeah, so we can see your questions in the chat if you post them. This is quite an unusual research, and so sometimes it's hard to really follow all the steps that are required. We do know that it's a difficult attack to pull off, but not an impossible one, as we've shown in this talk.
Thank you. If you have any questions, we're here to answer.
Okay, so there is one question here about POC scripts. This attack relies on a couple of elements other than code. And you need to have either a faulty cable or this type of EMP device, which we don't recommend that you build. It's quite dangerous. But we do have a white paper in which we detail how you can replicate this type of faulty cable, even in a simulated mode. And so you can go ahead and read the white paper. That can be a first step.
Okay, so there's a few questions about the EMP. So as far as shielded cables go, they're obviously better. And now I wouldn't say that they're completely impervious to this, because I did see it work on some shielded cables, but it works obviously a lot less, and I didn't really try to quantify how well it would work on shielded cables. Of course, cables that are shielded in the best possible way, which are STP cables, where every pair is shielded separately, fare pretty well. Also, the shield needs to be connected on both sides of the wire, and if it isn't, then that includes inside the sockets. So basically, the cable itself being shielded isn't exactly enough, but if everything is properly shielded, that means that it's a good shield and it's connected on both sides, reaching both terminals, then I would say it would be very difficult for that EMP attack to affect that cable. But again, I think it's a matter of just adding more power. You add more power and it will probably penetrate even those shields as well.
There's a couple of questions here about the range of the EMP. So we didn't really try to maximize this. In our small test of it, it was just about 3 meters or so of range. We do think that having an antenna, a directional antenna, unlike the one that we've used, would probably extend the range, and giving it more juice, more power, will also have a similar impact. So we do think that this can become something that works from more distance than what we've shown.
Yeah, but again, the EMP, all of this, it follows the inverse square rule, so it will never work for a very large distance. You can make it directional, but at these frequencies, I mean, you've seen the pretty big, like 2 meter tall antenna. In order to do this at a distance of 2 meters, and it's only directional. And now it wouldn't need to be longer, but to make it directional, like a Yagi antenna, for example, it would also need to be like 3 meters wide. But then it would work for a larger distance and be directional. But really, I mean, again, as a disclaimer, we're not exactly
experts in this specific field.
Yeah, and this field, it doesn't have all that much information freely available about it online, because again, there is no legitimate use for this kind of thing.
Right. The purpose of that part in our talk is to just demonstrate that it's theoretically possible. We came to a point where we have a device capable of interfering with the cable, but more research is needed to understand it really, what drives it, what are all causes for it to work better or worse. There is a question here about faulty cables, and I think then we need to finish. Okay, so
yeah, so we did measure, there's a question about measuring the signal strength inside the cabling. And yes, we used that electrical network analyzer device. We measured the signal loss in just standards compliant long cables. And then when attaching various faulty cables to them, there is a white paper. And while we didn't exactly publish, measurements of cables from our office, there is information there about what these cables, how strong the signal should be in those cables and such.
Yeah, and I think we need to stop at this point. Thank you for watching. Again, we have more info in the white paper on our website. It's armis.com/EtherOops if you're interested.
Thank you.
Thank you.